Hello everyone, welcome to a new episode of Inside DFINITY. On Inside DFINITY, we look at clips taken from DFINITY's internal global R&D meeting that takes place every week, where engineers and researchers show demos and talk about ongoing work. This week, we're going to look at a clip of a guy called Ulan, who's one of our senior engineers, talk about his work to remove bottlenecks from the persistent memory framework that enables smart contracts to maintain data. Now, smart contracts on the internet computer are actually composed of a bundle of WebAssembly bytecode and persistent memory pages that bytecode runs within exclusively. And each of these smart contracts is actually a software actor, which allows us to run any number of smart contracts in parallel deterministically. So a smart contract, the smart contract framework on the internet computer provides something called orthogonal persistence. And that means that when you create a smart contract, you can use any high-level language you like. The popular languages on the internet computer are currently Rust and a new built-for-purpose language called Motoko that compiles down to WebAssembly. And as a developer, you don't use a database or an API to maintain your data. For example, on Ethereum, the Solidity compiles down to EVM bytecode that maintains data by making SS store and sload calls. On the internet computer, you literally just write your code and in such a way that it does what you want, and just assume that it'll run forever. Okay, so your data persists in your variables, objects, collections, data types, which live in this persistent memory. And obviously, there's some interesting things you have to do when if you want to actually upgrade the smart contract, which is a possibility on the internet computer, if the controller ID is not set to 0. But we won't get into that now. What's important is that you write this high-level language, compiles down to WebAssembly, it runs in these persistent memory pages. The smart contracts are a software actor, which means that it communicates with other smart contracts by sending and receiving messages. These messages on the internet computer are actually function calls and function call results. And this is what allows the internet computer to run any number of smart contracts in parallel, because we enforce scheduling on the message passing to make it deterministic. And of course, all smart contract execution on a blockchain has to be deterministic. Now, as a consequence of being able to run any number of smart contracts in parallel, the internet computer is the world's first public blockchain to be able to actually scale out its single seamless smart contract environment so that it can host any number of smart contracts, run any number of smart contract computations, and host any amount of smart contract data. It's extremely efficient. Transactions or function calls that mutate contract state, I actually change that memory, get finalized in 2 seconds, which is, I believe, the fastest finalization speed in the world. By way of comparison, for example, Solana takes about 16 seconds to finalize transactions that mutate state. And transactions that in which mutations to state are actually discarded after they've run occur in milliseconds. And by leaning on this capability, we've been able to enable the internet computer to actually serve web content. So, on the internet computer, smart contracts can actually serve responses to low-level HTTP requests. And this provides for end-to-end decentralization where, we don't, a DApp really is a DApp. It's really Web3. The smart contract, smart contracts are, running the back end and maintaining the data and processing it in a tamper-proof and censorship-resistant way. But they're also directly interacting with the user by securely serving web content into their browsers. There's no cloud or anything like that involved. Now, all of this has changed the game, obviously. People are now building things like social networks and chat systems on the internet computer. And these things typically blend with DeFi. DeFi, of course, is already developing pretty fast. People want to build, fully decentralized exchanges on the internet computer. And growth is ferocious. You often hear me complaining about the paid crypto media. There's a lot of people in blockchain who are very worried about the internet computer. We don't get that much positive press, but thankfully developers can see through this. And in terms of the number of smart contracts running and the updates to smart contracts and the developers building and the number of dApps and most importantly the number of active users of those dApps, the internet computer is by far the fastest growing blockchain ecosystem. And that, of course, naturally, which is a good thing to have, has brought some challenges. So, I'm losing track of time now, but a week ago, 2 weeks ago, something like that. I think it was Icy Rocks. They did some kind of big NFT drop where they gave away 10,000 NFTs or something like that, and people descended en masse onto their dApp, and this really put the internet computer to the test. And as it happens, those parts of the internet computer, because it's internally sharded, you can't see it, using something called subnet blockchains that were actually serving the smart contracts behind the Icy Rocks dApp, started, getting congested and being unable to handle the volume of transactions. So, one way of dealing with that, of course, if you're Icy Rocks, is to adopt a different design that horizontally scales. But Icy Rocks should have easily been able to handle the load that was thrown at it. So, of course, there was a post-mortem. We looked into it, and as it turns out, there were bottlenecks in the persistent memory system that enable smart contracts to maintain data. So as it happens, we had put the system that's described into the nodes because we knew it was secure and stable, and we wanted to get the network live. But it's suboptimal with respect to performance. So we needed to sort of hot fix this and improve its throughput pretty quickly, because it's going to take a while for this other persistent memory system we've been working on before it's ready. So Ulan has been working on this. He's a very smart developer, and he's going to tell you how he's improved the performance of the current persistent memory system, and he's got really huge speed ups. So let's watch and listen to what Ulan has to say.
Next then is ongoing work, and we start with memory management. We all heard about performance issues in production, and Ulan can explain us more what has happened and what the current improvements are.
Mm-hmm. Right. Hi. Right. So there is ongoing incident or code yellow due to one subnet being very slow, and we identified that the root cause is a bottleneck in our memory system. And today, I want to explain the problem in a bit more detail and also explain the solution that's going to roll out this week. So the first thing is to reproduce the problem, and to do that, I created a simple canister. It has 1 GB of memory, and on each message, it copies half of that memory to another half. So it moves a lot of data. And running it on existing with the existing code, it takes about 3 seconds. Now, this subnet has a lot of canisters, right? And it's interesting to see how it behaves when there are multiple canisters running in parallel. And if we go to the next slide, so this is a workload I did for multi-threaded testing, where I created 2 copies of the same canister and then sent them the messages, many messages, so they run in parallel. And thinking logically, the expectations is this case is best case for parallelization, right? Because canisters are independent and we can run messages in parallel. So ideally, the average message duration should not change. So it should remain 3 seconds. Then if there is a bottleneck, assuming that the messages sequentialize with each other, like, and they have to be executed like interleaved, in the worst case, like expectation is 9 seconds. And in the next slide, we see what happens in practice. So in practice, like this agrees it's worse than the worst case. It's 25 seconds, like just adding 2 canisters increases the message duration like almost 10x. And this is what we saw on that subnet. And in this graph, like the graph shows like the how I was deploying and starting the sending messages to that canister. Like on the left, we see the first canister where average message duration was 3 seconds. If I add another canister, the same workload starts sending messages, like it jumps to 17 seconds and then 25 seconds for third. Like I also tried adding more, so it increases with more canisters, it increases more. So there is something wrong going on here, something off. And to explain that, I would need to get a bit into technical details. I'll try to keep it on the high level. So like on the next slide, there will be our memory system. Like, so when we start executing a message, like we create a WebAssembly instance, and we start with a kind of empty memory for that WebAssembly instance. But the canister has already its own memory from the state. And the state currently consists of 2 parts. Like there is a checkpoint file that represents the memory of the canister at the last checkpoint. And then on top of it, there is an overlay, which is called page delta. These are the pages that were modified since the last checkpoint. And then we have this code called signal handler, and its responsibility is as the WebAssembly code is running, it needs to fetch pages from the canister state to the WebAssembly memory. And second responsibility is it also needs to keep track of pages that the WebAssembly instance modified so that they can be added to the page delta for the next execution. Like just to show you a concrete example, like on the next slide, let's assume the canister just writes something on the first page. Then we get a signal handler because all the memory is set up in such a way that accesses are disallowed. So there is a way to set protection flags. And on the first access, we get a signal handler. And on the next slide, like signal handler will see that the memory is empty. It copies over bytes to that page. Then, since it has to keep track of dirty pages, dirty meaning modified pages, then it sets protection flags such that this page becomes read-only on the next slide. So it's read-only and then continuous execution. And if the access was for write on the next slide, it will actually get another signal and it will do another call to operating system to set up protection for the page properly. So these calls to the operating systems are expensive. Like I call them syscalls here, system calls. And after that, like this page is now done, meaning that now application can modify it and the modifications will be fast. And if we imagine the workload where an application is just writing a lot of data sequentially, like on the next slide, we will see like that we get a lot of signals, like for 8 pages, like we get 16 signal calls and then 24 calls to the operating system calls. And I know that the main problem here and the source of the bottleneck are the system calls. And I know that because I wrote a separate like C++ program that mimics this behavior and doesn't use any signal handler and let it run in multiple threads. And it shows a similar slowdown with more threads added. So the problem here is like that we have, for each page, we are calling just too many system calls. And so that's what we have like or had when we had the incident. And on the next page, on the next slide, we will like this is the approach I took. Like we needed a quick solution. Like it had to be like done in days, like not months, right? So for that reason, I decided to stick to the existing state representation that we already have that works, but optimize a lot, like push optimization as much as possible in the signal handler. And there are a couple of ideas that I will briefly explain now. Like on the next slide, this is the idea that I first heard from Roman, then Alin told me also independently, and it's all based on the previous work by Kiran. So the idea is, since we have this checkpoint file, and there is a very easy way to, there's an operating system primitive that allows to map big portions of that system checkpoint file to the WebAssembly memory without paying for copying. So that's the idea of like map chunks of checkpoint files onto the WebAssembly memory and use copy on write protection. And this helps for cases when canister reads a lot of data, but for keeping track of modified pages, we still need to keep track of that on the page level. So on the next slide, if you have the previous workload that still writes to each page, we will still get a lot of system calls. Now, how we can get rid of this, or like optimize keeping track of dirty pages. So on the next slide, there is next optimization. It is applicable only for queries because, as you know, queries do not modify the state, right? So they kind of read-only operations. And it makes sense to not keep track of dirty pages for them because we throw away the state after executing the query anyway. Well, that's in theory. Like in practice, we have this prototype of intercanister query calls, which makes queries very expensive because in order to implement that, queries become similar to updates, so they become as expensive as updates. And this is very unfortunate because this prototype, like intercanister queries, are not spec'd currently, but we still ship a prototype, and 2 subnets use these queries, and these queries are 5% of all other queries. So this 5% is slowing down like all other queries. I found a workaround where I kind of reshuffle and make these intercanister queries more expensive, but the normal queries faster. So this is one optimization, to not keep track of dirty pages for queries. And on the next slide, I think the most impactful, before we go there, this is the same workload, but running for a query, like the number of syscalls reduced to 6 from 17. And on the next slide, I think this is the most impactful optimization is for updates. We still need to keep track each page individually. And in order to reduce number of signals and system calls, what we can do is we can actually prefetch, like when there is a signal coming in, instead of handling only the single page, we can handle a bunch of pages first. And but that is a bit dangerous because this prefetching could be a redundant work. Like imagine if a message only accesses a single page, only writes to the single page, and we prefetch multiple pages and marks them dirty. We would do a lot of work that would be redundant. And like another idea here is to amortize the dirty pages, meaning that we will, when we look at the page, we will also check how many pages were dirtied before it. And that would be our upper bound on how many we can prefetch. And I also added a separate upper bound, like constant 32, which is like chosen conservatively so that we don't prefetch a lot. And when I say prefetching dirty pages, after execution, we still need to verify that the pages that were prefetched as dirty, they are actually dirty, that meaning that they were modified. And that verification is done by just running like mem compare of that speculatively prefetched page with the original contents. And on the next slide,
Ulan, 30 seconds left.
Yep. Okay, let's keep this. Let's go to the results. Right. This next slide would be the result. So this shows that the actual problem that I mentioned at the beginning, where update call taking 25 seconds with 3 canisters, is solved. So now it takes 1.8 seconds. And for single-threaded case, there are still improvements. And I did performance evaluation to ensure that I check like tiny queries, medium-sized queries, and large queries to ensure that I don't regress any case. And I see improvements, like in most cases, like only tiny queries do not improve as much, but others improve by 2x or 3x. And there is a conclusion on the last slide, like this is a current state. Like I put a link to actual work that was done. It will be in this release that's shipping, like rolling out this week. It's only Linux because of like platform-specific bits that I used. macOS still uses old signal handler. And thanks to all folks who helped with discussions and reviews.
Thank you, Ulan.